Today we're going to be solving October-November 2023 paper 22. Question number 1 says the elements silicon, phosphorus and sulfur are in period 3 of the periodic table. Describe the variation in atomic radius from silicon to sulfur. So this question is asking what happens to the atomic radius across the period. We know that it decreases across the period, right? And we don't have to explain it because it's only asking for a description, but the explanation is that because the number of shells remains the same, whereas the nuclear charge increases, right? So if the nuclear charge increases or the number of protons increases, then obviously the valence electrons experience a stronger nuclear attraction. So the electrons are held more closely to the nucleus. So silicon has a macromolecular structure. Okay, silicon has a macromolecular or giant covalent structure, and because it has a macromolecular structure, right, a lot more energy is needed to break the covalent bonds, right? So macromolecular structure or giant covalent structure, all the atoms are held by covalent bonds, right? Whereas sulfur has a simple molecular structure. Okay, simple molecular structure. You would also say that a lot more energy is needed. A lot more energy is needed to break the covalent bonds. Between silicon atoms than the van der Waals forces or intermolecular forces between sulfur molecules, right? Because sulfur has a simple molecular structure, the molecules are held by weak van der Waals forces, okay, or weak intermolecular forces. Table 1.1 shows some properties of the element silicon to sulfur. The first ionization energy of phosphorus is not shown. Complete table 1.1 to show the total number of s and p electrons in an atom of silicon, phosphorus and sulfur. So if you look at the periodic table, right, what's the electronic configuration of silicon? Silicon is 1s2, 2s2, 2p6, and then 3s2, and then 3p2, right? Phosphorus is 3p3, and then sulfur is 3p4, okay? So what do we have here? Okay, for all of them we have 1s2, 2s2, 2p6, and then 3s2, and then for silicon, right, for silicon we have 3p2. Okay, for silicon we have 3p2. So the total number of electrons in s subshells, we have 2 in the 1s subshell, 2 in the 2s subshell, and 2 in the 3s subshell. So that's 6. Same for phosphorus, same for sulfur, right? But then for the p subshell, silicon has 6 plus 2, which is 8. Okay, that's 8. Phosphorus is 3p3, so that would be 9. And then sulfur is 3p4, so that would be 10, right? 6 in the 2p subshell, and then 4 in the 3p subshell, right? 4 in the 3p subshell. Constructing an equation to represent the first ionization energy of sulfur. The first ionization energy is when 1 mole of electrons is removed from 1 mole of gaseous atoms to form 1 mole of gaseous 1 plus ions. 3 possible values for the first ionization energy of phosphorus are given. Circle the correct value. Explain your choice, including a comparison of your chosen value to those of silicon and sulfur. Now the value for silicon given to us is 786 and the value for sulfur is 1000. Okay, so I'll write that down. For silicon, the value given to us is 786, and then for sulfur, the value given to us is 1000. So where do you think phosphorus is? Now if you guys remember, silicon is 3p2, right? It ends with 3p2, so it's argon and then 3p2. And then sulfur is argon 3p4, right? The configuration, whereas phosphorus is argon 3p3. Now if you guys remember, the first ionization energy increases across the period. Why does it increase across the period? Because again, The number of shells remains the same, shielding remains the same, but the nuclear charge increases, right? We have a stronger attraction towards the valence electrons. But from phosphorus to sulfur, we have an exception, right? So if you guys remember the trend for first ionization energy versus atomic number, right? Across the period, you have an increasing trend, but there's a decrease. There's a decrease from magnesium to aluminum, and there's a decrease from phosphorus to sulfur. Why is there a decrease? Because phosphorus is 3p3 and sulfur is 3p4. So what you have is in phosphorus, all your electrons are unpaired. Okay, all your electrons are unpaired, whereas in sulfur we have a pair of electrons. So what we would say here is that, so what we'd say over here is that the first ionization energy of phosphorus is 1060 kilojoules per mole. Okay, right? It would be higher than sulfur, and the reason why is because one of the 3p orbitals, okay, one of the 3p orbitals in an atom of sulfur has paired electrons, okay, or a pair of electrons. Therefore, the outer electron is easier to remove. Okay, therefore, the outer electron is easier to remove due to spin pair repulsion. Okay, electron is easier to remove due to spin pair repulsion. And we also have to make a comparison to silicon. Okay, you have to make a comparison to both, because the question says include a comparison of your chosen value to those of silicon and sulfur. So we've explained why it's more than sulfur, and the reason why it's more than silicon is because it's just the general trend, right? The general across the period trend. The reason it's greater than sulfur, right? The reason it's greater than sulfur is because phosphorus has a greater nuclear charge than silicon, whereas the number of shells, and therefore shielding remain the same, right? Are similar. Hence, the valence electrons in phosphorus experience a stronger nuclear attraction. Okay, the valence electrons in phosphorus experience a stronger nuclear attraction. SiCl4 and PCl5 each react with water, forming misty fumes. Identify the chemical responsible for the misty fumes. The chemical is HCl, or hydrogen chloride. Okay, don't say hydrochloric acid. Okay, hydrogen chloride, right? The gas. And predict the shape of the SCl2 molecule. Now for SCl2, sulfur is in group 16, so it has 6 valence electrons. It's making 2 single bonds with chlorine. Okay, so it has 6 valence electrons, making 2 single bonds with chlorine, and then it has 4 more electrons. So 1, 2, 3, 4. Right? Again, sulfur is in the same group as oxygen. Okay, it's in the same group as oxygen. So similar properties, right? Similar shape to what we have with H2O. Okay, similar shape to what we have with H2O. So the shape is called bent. Okay, you can say bent, angular, V-shaped, nonlinear. Okay, bent, nonlinear, angular. Okay, these are all acceptable answers. So here we have question number 2. Nitrogen monoxide and nitrogen dioxide react at 25 degrees Celsius to give N2O3 as shown in the equation. Okay, so they've shown this equation here. The reaction is reversible and reaches equilibrium in a closed system. Figure 2.1 shows how the rate of the forward reaction changes with time. Initially, the rate of the reverse reaction is 0. Complete figure 2.1 to sketch how the rate of the reverse reaction changes with time. So initially we have no N2O3, so the rate of the backward reaction, or the rate of the reverse reaction is 0, right? Now over time what happens is that as nitrogen monoxide and nitrogen dioxide react, the rate of the forward reaction starts to decrease, right? Because you have lesser of NO and NO2, but as more and more N2O3 is produced, the rate of the backward reaction starts to increase. The rate of the backward reaction starts to increase, and at equilibrium, the rate of the backward reaction is equal to the rate of the forward reaction, right? That is what dynamic equilibrium is by definition. And the rate will become constant at the same time. Okay, they're going to become constant at the same time. Okay, because obviously that's the point at which dynamic equilibrium is reached, right? So when the rate of the forward reaction becomes constant, at the same point the rate of the backward reaction become constant, and the two rates will be equal. Okay, that's what we mean by dynamic equilibrium. State how the position of the equilibrium changes, if at all, when the reaction takes place at 100 degrees Celsius. Explain your answer. Assume that the pressure remains constant. So they've mentioned that this reaction is taking place at 25 degrees Celsius. It's taking place at 25 degrees Celsius, and it's an exothermic reaction. It's an exothermic reaction. So if you increase the temperature, okay, if you increase the temperature to 100 degrees Celsius, which direction will the equilibrium shift in? The equilibrium will shift to the left, because an increase in temperature will favor the endothermic direction. Okay, an increase in temperature will favor the endothermic direction, which is the backward reaction. So over here we're going to say that the equilibrium will shift to the left. The equilibrium will shift to the left. Okay, or you can say that it's going to shift in the backward direction, because an increase in temperature will favor the endothermic direction. Right? In this case, the endothermic direction is the backward reaction. Okay, that's the backward or the reverse reaction. The backward reaction. Table 2.1 shows the composition of an equilibrium mixture of nitrogen monoxide, nitrogen dioxide, and N2O3 at 101 kilopascals. Calculate Kp, the equilibrium constant with respect to partial pressures, and deduce the units of Kp. Now Kp, the equilibrium constant with respect to partial pressures, is the partial pressure of N2O3, okay, the partial pressure of N2O3 divided by the partial pressure of NO2 times the partial pressure of NO. Okay, this is based on the equation given to us, which is NO plus NO2 gives us N2O3, right? So again, it's the partial pressure of the products to the power of 1 in this case, right? Divided by the partial pressure of the reactants, that would be NO and NO2, again to the power of 1. Now, how do we get the partial pressure for each of these gases? The partial pressure is the mole fraction times the total pressure. What is the mole fraction? The mole fraction is the number of moles divided by the total number of moles. So for example, if I wanted to find the partial pressure of N2O3, you would take the mole fraction of N2O3, that's the moles of N2O3, that's 0.390 divided by the total number of moles. Okay, the total number of moles over here is 1.6. Okay, so we have a total of 1.6 moles of gas. You can just add up the number of moles of each gas. Okay, so this is the mole fraction. This is the mole fraction of N2O3. And you multiply this by the total pressure. The total pressure is 101 kilopascals. So you get the partial pressure of N2O3. You get the partial pressure of N2O3 as 24.62 kilopascals. Okay, 24.62 kilopascals. And then the partial pressure of NO is equal to the partial pressure of NO2. Is equal to the partial pressure of NO2. And that again is the mole fraction. Right, that's the number of moles. That's the number of moles of NO, or the number of moles of NO2 divided by the total number of moles times the total pressure, and this gives us the partial pressure as 38.19 kilopascals. Okay, 38.19 kilopascals. And we just plug that into the Kp expression. So Kp is equal to 24.62. That's the partial pressure of N2O3 divided by 38.19 times 38.19. So that's 38.19 squared, and that gives us Kp as 0.0169. 0.0169, and the units for Kp are pressure divided by pressure squared, which is 1 over pressure. Right? We have pressure in the numerator, pressure squared in the denominator, so 1 over pressure, and in this case the units of pressure are kilopascals, so the units will be kilopascals inverse, right? That's pressure inverse. So the units are kilopascals inverse. Identify one natural process and one man-made process that cause the formation of atmospheric nitrogen monoxide and nitrogen dioxide. So oxides of nitrogen are made when nitrogen and oxygen react. Okay, nitrogen and oxygen react at a very high temperature. Okay, now naturally that happens in the presence of lightning. Okay, because when you have lightning, you have a high enough temperature for the triple bond in nitrogen to break and react with oxygen to form oxides of nitrogen. Or in cars, okay, in combustion engines, where you have very high temperatures, so that provides enough energy or provides the activation energy for nitrogen to react with oxygen. NO2 is a brown gas that can be used to form nitric acid. NO2 is a free radical, defined free radical. It's a species with one or more unpaired electrons, okay, with at least one unpaired electron. Okay. They're generally highly reactive. Okay, they're highly reactive species with at least one unpaired electron. NO2 has a catalytic role in the oxidation of atmospheric sulfur dioxide. Write equations to show the catalytic role of NO2 in this oxidation. So nitrogen dioxide can react with sulfur dioxide, okay, to form nitrogen monoxide and sulfur trioxide. Okay. Now normally sulfur dioxide does not react directly with oxygen to form sulfur trioxide. Okay. You need a catalyst for that to happen. So in this case, nitrogen dioxide is the catalyst. Okay, it reacts with sulfur dioxide. This reaction has a relatively low activation energy than the reaction of sulfur dioxide with oxygen directly. Okay, and then obviously since NO2 is the catalyst, it's going to be regenerated. Okay, it's regenerated when nitrogen monoxide reacts with oxygen, okay, to form NO2. Okay, so here we show that nitrogen monoxide is an intermediate formed in the first step, reacts in the second step, and nitrogen dioxide initially reacts with the sulfur dioxide and it's regenerated at the end. Okay, so it's a catalyst. So if you were to write the overall equation for this reaction, you would get this equation. Okay, you get SO2 plus half O2. Okay, SO2 plus half O2 gives you SO3. Okay, so this is the overall equation for this reaction. State one environmental consequence of the oxidation of atmospheric sulfur dioxide. So when sulfur dioxide is oxidized, it forms the sulfur trioxide. Okay, and sulfur trioxide reacts with H2O to form sulfuric acid. Okay, this happens when rain falls. So this type of rain is called acid rain. Okay, so the environmental consequence of the formation of sulfur trioxide, okay, is the formation of acid rain. A student titrates nitric acid with a base to form a solution containing aqueous magnesium nitrate. Identify a base that the student could use. So you want to react nitric acid, okay, you want to react nitric acid with a base to form magnesium nitrate. Okay, so your base has to contain magnesium, so a suitable base would be magnesium hydroxide. Okay, a suitable base could be magnesium hydroxide. You react magnesium hydroxide with nitric acid, you get salt and water, right? So you get magnesium nitrate and H2O. The student evaporates the water to obtain magnesium nitrate solid. When this solid is heated, it decomposes. Write an equation for the decomposition of magnesium nitrate. So magnesium nitrate is MgNO3 twice. Okay, Mg is 2 plus, NO3 is 1 minus, guys, so it's MgNO3 2. And when this decomposes, you get magnesium oxide, you get nitrogen dioxide, and you get oxygen gas. Okay, to balance this equation, you're going to have 2NO2 and half O2. Okay, you just have to remember this equation. What's an observation in this reaction? You're going to observe the formation of a brown gas. Okay, a brown gas, that's nitrogen dioxide. Okay, it's a brown gas. State how the thermal stability of group 2 nitrates changes down the group. The thermal stability of the group 2 nitrates increases down the group, which means a higher temperature is needed for their decomposition. Question number 3 says phosphoric 5 acid, H3PO4, is used in both inorganic and organic reactions. H3PO4 is made in a two-step process from phosphorus. In step 1, phosphorus reacts with an excess of oxygen to form a white solid. In step 2, the white solid then reacts with water to form H3PO4. Write an equation for each step. So phosphorus is P4. Okay, phosphorus is P4. It reacts with oxygen to form P4O10. Okay, that's phosphorus 5 oxide. Okay, phosphorus 5 oxide. We need 5O2. And then the P4O10 reacts with H2O to form phosphoric acid. So that's H3PO4. And then you have 4 phosphorus on the left, so you're going to have 4 phosphorus here. And then you have 12 hydrogens here, so you're going to have 6 H2O. So phosphoric 5 acid, H3PO4, is a weak Bronsted-Lowry acid. Define weak Bronsted-Lowry acid. Now when we say Bronsted-Lowry acid, we mean that it's a proton donor. And the word weak over here, okay, the word weak means that it partially ionizes. So here we'd say that it is a proton donor. Okay, it is a proton donor. Okay, that's what we mean by Bronsted-Lowry acid. Okay, it's a proton donor that partially ionizes in solution. Okay, that partially dissociates. Okay, that partially dissociates or partially ionizes in solution. Okay, that's what we mean by weak. So weak acid, okay, donates a proton and partially ionizes in solution. Okay, so this is the acid part and this is the weak part. Part B says phosphoric acid is also formed in the process shown in reaction 1. Table 3.1 shows some relevant thermodynamic data. Here they've given you the data on the enthalpy change of the formation of the reactant and the products. Okay, the first part says define enthalpy change of formation. The enthalpy change of formation is the enthalpy change. It is the enthalpy change when 1 mole, okay, when 1 mole of a substance, okay, when 1 mole of a substance is made, okay, from its constituent elements, in their standard states. In their standard states. Okay, their standard states are the states at 298 Kelvin and 1 atmosphere. If the question says define the standard enthalpy change of formation, if the question says define standard enthalpy change of formation, in that case you would have to say when 1 mole of a substance in its standard state, okay, you would have to specify the substance being in its standard state as well. Okay, if the question was asking for standard enthalpy change of formation, then the substance also has to be in its standard state. Okay, but for just enthalpy change of formation, the substance doesn't have to be in a standard state, but the elements have to be in their standard states. And if it's a standard enthalpy change of formation, you also have to mention under standard conditions. Okay, so the reactants and the products are under standard conditions. So you have to say under standard conditions at the end if it was asking for standard enthalpy change of formation. Use the data in table 3.1 to calculate the enthalpy change of the reaction of reaction 1. Okay, so we go to the table. Using this data, we have to calculate the enthalpy change of this reaction. So I'm just going to take that reaction. I'm going to take the table. Okay, so this is the table. We have this data over here. We're going to need this for the question. So we take this down, right? So they've given us the reaction. They've given us the data. Okay. Now you guys should know that the enthalpy change of a reaction, okay, the enthalpy change of a reaction is the enthalpy change of formation of products minus the enthalpy change of formation of the reactants. Okay. If they've given you enthalpy change of formation data, you can find the enthalpy change of a reaction in terms of the formation of the products and the reactants. Okay. They've given you formation data, you can just say formation of products minus formation of reactants. In this case, your products here are H3PO4. You have 3 moles of that. So that will be 3 times the formation of H3PO4. That's 3 times negative 1281 plus the formation of PH3. That's 9, right? We just have 1 mole of that, plus 9, minus the formation of the reactants. So here we have 4 moles of H3PO3. So we have to subtract that. So minus 4 times minus 972. And that gives you the enthalpy change of the reaction as positive 54 kilojoules per mole. So that's your answer. Explain why reaction 1 is a disproportionation reaction. Explain your reasoning with reference to relevant oxidation numbers. Now, a disproportionation reaction is a reaction in which a single species undergoes both oxidation and reduction simultaneously. Okay, now in this reaction, oxygen is -2 throughout and hydrogen is +1 throughout, right? So that means that it must be the phosphorus that's undergoing disproportionation, okay? And we can check. Now, if you talk about H3PO3, right, phosphorus has an oxidation number of +3. You can check that the hydrogens are +1. You have 3 hydrogens. You have 3 oxygens, which are -2. You have 3 oxygens, which are -2. And then you have phosphorus, which is, let's say, X. And that gives you X as +3. So the oxidation number of phosphorus initially, is +3, right? And then in H3PO4, phosphorus is +5, okay? They've said that this is phosphoric 5 acid, okay? So phosphorus is +5. So here phosphorus is +5. You can calculate that as well. You have 3 hydrogens, which are +1, right? So +1, +1, +1, that's +3. You have 4 oxygens, which are -2 each. So +3 and then -8, so that's -5. So phosphorus is +5. Okay. But in the question, they've said that this is phosphoric 5 acid. So you don't need to calculate it. Okay, but you can. And then in pH3 over here, okay, that's phosphine. Okay, pH3 phosphorus is -3. Okay, phosphorus is -3 because the 3 hydrogens are +1 each. So +1, +1, +1, that's +3. So phosphorus must be -3. So we can clearly see that phosphorus is undergoing both oxidation and reduction, right? It's being oxidized from +3 to +5 and is being reduced from +3 to -3. So why is this a disproportionation reaction? Because phosphorus, okay, is both oxidized and reduced, okay, and reduced. It's oxidized from +3 to +5 and reduced from +3 to -3 simultaneously. Okay. The part C says figure 3.1 shows a reaction scheme that involves phosphoric acid in several reactions. Identify A, which reacts with propene in the presence of phosphoric acid in reaction 2. So in reaction 2, propene is being converted to propan-2-ol. So what would the reagent be for this reaction? Phosphoric acid is the catalyst, okay? The reagent here would be steam, okay? You can say H2O as well, okay? But specifically it's gaseous H2O, right? Alkenes react with steam in the presence of phosphoric acid catalyst to form alcohols, right? This is known as the hydration. This is known as the hydration of alkenes, okay? And this is an electrophilic addition reaction. Draw the structure of B. Okay, draw the structure of B. So what happens when propan-2-ol reacts with KBr and phosphoric acid? So in this case, you would get a substitution reaction. Okay, you get a substitution reaction. When KBr reacts with phosphoric acid, okay, they end up making HBr, and then the HBr reacts with the alcohol. Okay, the HBr reacts with the alcohol, and the bromine, okay, the bromine replaces the OH. Okay, the bromine replaces the OH. So you get a substitution reaction. Okay, so what we have here is the alcohol is converted into a bromoalkane. Okay, so the OH is replaced with a bromine. Name the type of reaction that occurs in reaction 3. So in reaction 3, the alcohol is being converted into an ester. Okay, propan-2-ol is reacting with ethanoic acid. Okay, propan-2-ol is reacting with ethanoic acid, a carboxylic acid, to form an ester. So this reaction is called an esterification reaction. Okay, you can also refer to it as a condensation reaction. You can say esterification or you can say condensation. Okay, it's a condensation reaction. Reaction 3 is monitored using infrared spectroscopy. It is not possible to use the OH absorption frequency to monitor the reaction. Use table 3.2 to identify a suitable bond whose absorption frequency can be used to monitor the progress of reaction 3. State the change you would see in the infrared spectrum during reaction 3. Now, in this reaction, okay, in this reaction over here in reaction 3, you're converting the alcohol to an ester, okay, in the presence of a carboxylic acid. Now they're saying that you can't really monitor the OH peak here, okay, you can't really use the OH peak to monitor the progress of the reaction. So what can we use over here? We can use the C double bond O peak, right? The reason we can use the C double bond O peak is because the C double bond O absorption for an acid is slightly different from the absorption for an ester. Okay, this is not a very good way to monitor the reaction because there is some overlap in the peaks. But what's happening here is this, okay? I'm going to write down the reaction. So what we have is, we have CH3, CHOH, CH3. Okay, that's propan-2-ol reacting with ethanoic acid to give you an ester, right? You get an ester and H2O. Okay, the ester over here is CH3, C double bond O, and then you have O, and then you have CH, CH3 twice. Okay. Now, what we're saying here is that initially with the acid, right, we have a C double bond O. The C double bond O has a shift. The C double bond O has a shift in the range 1670 to 1740 wave numbers. And then as the ester forms, the C double bond O, के shift की value changes. Okay, C double bond O की shift की value goes from 1670 to 1740 to 1710 to 1750. Okay, so there's basically an increase. Okay, there's an increase in the frequency at which the C double bond O bond absorbs. Okay, in the spectrum. Okay, so there's an increase in the absorption frequency. So the bond we're going to use is the C double bond O. The bond we're going to use is the C double bond O, and the change is that there's an increase in the absorption frequency. Okay? There's an increase in the absorption frequency from 1670 to 1740 wave numbers to 1710 to 1750 wave numbers. H3PO4 also reacts with alcohols to form organophosphates. Organophosphates are compounds similar to esters. They have the general structure shown in figure 3.2. Now in organophosphates, okay, we see this POOR, right? This is similar to what we see in esters. In esters, we have a COOR, right? Now instead of a carbon here, we just have a, instead of a carbon here, we have a phosphorus, okay? Instead of a carbon here, we have a phosphorus. So that's basically what organophosphates have. Okay, so phosphoric acid, okay, phosphoric acid has this type of a structure. Okay, this is phosphoric acid. You have H3PO4. Okay, this is what it looks like. So you have H3PO4. And when you react this with methanol, okay, when you react this with methanol, okay, similar to what you had with esterification, right? You have an ester form over here. Now, with esterification, if you guys remember what happens, the oxygen from the alcohol bonds to the C double bond O from the acid. Okay, the oxygen from the alcohol bonds to the C double bond O from the acid. And what do you end up getting? Well, the OH is removed from the acid and the H is removed from the alcohol. Okay, so a similar thing will happen here. What will happen is that the alcohol will react with this phosphorus, okay, and the oxygen will bond to the P double bond O. Okay, the oxygen will bond to this phosphorus, similar to how it does with carboxylic acid, right? The oxygen from the alcohol bonds to the C double bond O. Here, the oxygen from the alcohol will bond to this phosphorus. Okay, so what do we end up getting? Well, what we end up getting here is this, right? What we end up getting is P double bond O, and then oxygen. Okay, this oxygen comes from the alcohol, right? So this P double bond O bonds to the oxygen from the alcohol, so we get O and then CH3. Again, oxygen bonds to this phosphorus, oxygen bonds to this phosphorus, so we have O and then CH3. And then again, oxygen bonds to the phosphorus, so we have OCH3. Okay, so we have to show this reaction. Okay, we have to write the equation for this reaction. So what do we end up getting? We have 3 of these CH3Os, right? We have CH3O thrice bonded to this phosphorus, so PO. And then obviously, since we're making 3 of these bonds, right, for every 1 bond you remove 1 H2O, right? Again, this guy loses the OH, this guy loses the H, right? And we have 3 of these. We have 3 of these, so we get 3 H2O. Okay, we get 3 H2O. Compound T is a simple organophosphate. The mass spectrum of T shows a molecular ion peak at a mass to charge ratio of 182. This peak has a relative intensity of 12.7. Relative intensity is analogous to peak height. Okay, the relative intensity of the M plus 1 peak is 0.84. Relative intensity of the M plus 1 peak is 0.84. Deduce the number of carbon atoms in T and hence suggest the molecular formula of T. Assume that phosphorus and oxygen exist as single isotopes. So the molecular ion peak is also referred to as the M peak or the M plus peak, right? And we know that the ratio of the M plus 1 to the M peak is 1.1 N over 100, okay? You have to remember this formula. The ratio of the abundances, okay, the ratio of the abundances or the heights, okay, the ratio of the heights of the M plus 1 and the M peak is equal to 1.1 N over 100, where N is the number of carbon atoms. So we can calculate the number of carbon atoms here, right? The intensity or the height of the M plus 1 peak is 0.84. Okay. The height of the M peak is 12.7. Okay, and this is equal to 1.1 N divided by 100, okay, which gives us N as 6 carbon atoms. Okay, so we have 6 carbon atoms here. Okay, so we have 6 carbon atoms, so that's C6. Okay, it's an organophosphate, so we have 1 phosphorus. Okay, we have 1 phosphorus here. Now we need to figure out the number of hydrogens and oxygens. Okay. Now carbon has an atomic mass of 12, so we have 6 carbon atoms, so those have a mass of 72. We have a phosphorus, which has an atomic mass of 31. So 72 and 31 gives us 103, right? They've also told us that the M peak, okay, the M peak is at 182. Okay, so the MR is 182. Okay, so 103 for the 6 carbons and the phosphorus. If we do 182 minus 103, right, we're left with a mass of 79. The 79 covers the hydrogens and the oxygens. Okay, the 79 covers the hydrogens and the oxygens. Now, oxygen obviously has a relative atomic mass of 16. Okay, oxygen has a relative atomic mass of 16. So, how many oxygen atoms would we have? Well, we're going to have 4 oxygen atoms, right? We're going to have 4 oxygen atoms because we can't have 5, right? 5 oxygen atoms would have a mass of 80. So that would exceed the MR, right? The 79 has to cover the hydrogens and the oxygens. So if we have 4 oxygen atoms, right? 4 oxygen atoms would have a mass of 4 times 16, which is 64, and that leaves us with 15 hydrogen atoms, right? That leaves us with 15 hydrogen atoms. So then the molecular formula is C6, right? The molecular formula is C6. We have 15 hydrogens, so H15. We have 4 oxygens, so O4, and then we have a phosphorus. Okay, and the number of carbon atoms is just 6. So here we have question number 4, which says lactic acid and pyruvic acid both contain 2 functional groups. Explain why lactic acid exists as optical isomers. Now, optical isomerism arises when a compound has a chiral center, right? A chiral center is a carbon atom that's bonded to 4 different atoms or groups of atoms, right? So here, this carbon is a chiral center. Bonded to a hydrogen, a CH3, an OH, and then a CO2H, right? So the reason why lactic acid exists as optical isomers is because it has a chiral center, okay? It has a chiral center, right? Which is a carbon atom bonded to 4 different atoms or groups of atoms. Give the systematic name of lactic acid. Now, lactic acid has a 3-carbon chain. Okay, it has a 3-carbon chain, right? The highest priority would go to the carboxylic acid, right? The carboxyl carbon, that would be carbon 1, carbon 2, and then carbon 3, right? So what we have here is propanoic acid. Okay, propanoic acid. Okay, you don't have to number the carboxylic acid in the name because carboxylic acid will be carbon number 1 by default, right? Automatically. And then on carbon number 2, we have an OH group. Okay, on carbon number 2, we have an OH group. So that makes this 2-hydroxy propanoic acid. Okay, 2-hydroxy propanoic acid. Right, so again, 3-carbon chain, right? 3 carbon chains means prop, carbon carbon single bond, so AN, so propan, and then carboxylic acid gets priority, okay, in the naming and the numbering. So it gets carbon number 1 by default because carboxylic acid will always be on carbon number 1, so propanoic acid, and then the OH group is on carbon number 2. Okay, so that will be 2-hydroxy propanoic acid. Lactic acid forms hydrogen bonds with water. Complete figure 4.2 to show the formation of a hydrogen bond between one molecule of lactic acid and one molecule of water. Label the hydrogen bond, show any relevant dipoles and lone pairs of electrons. Okay, so you have to show a hydrogen bond with a water molecule. I'll just show it here. Okay, so we have this, right? So here we have a water molecule, and then you show this dotted line, right? Like this. You have to show the partial charges, delta minus, delta plus, delta minus, and then label the hydrogen bond. Okay. Now again, I should clarify that this hydrogen bond should be shown in a straight line. Okay, this hydrogen bond should be shown in a straight line with this covalent bond. The hydrogen bond has to be shown from the lone pair of the oxygen to the hydrogen. Okay, it should be shown from the lone pair to the hydrogen. And you have to show the partial charges on the hydrogen and the 2 oxygens either side. 2 possible syntheses of pyruvic acid are shown in figure 4.3 and figure 4.4. Complete the diagram in figure 4.5 to show the mechanism for the reaction of propene with bromine. Okay, so propene with bromine is an electrophilic addition reaction. We have to show the mechanism for the reaction between propene and bromine, right? So here again, you should show the partial charges on the bromine. We have Br delta plus, Br delta minus. Okay, this dipole is induced. Okay, this dipole is induced due to the repulsion of the electrons in bromines from the electrons in the double bond. Okay, the electrons in the double bond repel the electrons in the bromine. Okay, they repel the electrons in the bromine further away towards this bromine. So you have to show the partial positive on this bromine, the one closer to the alkene, and the partial negative on the bromine further away. Okay, this is an induced dipole, and then you have to show a curly arrow from the pi bond to the bromine, a curly arrow from the pi bond to the bromine, curly arrow from this bond to this bromine. Okay, this is called heterolysis. Okay, the bond breaks, both the electrons go to this bromine. What you end up with is a carbocation intermediate, right? This carbocation intermediate is favored because this is a secondary carbocation intermediate. Okay, so you can have the first bromine go here or here. Preferably, you should show the secondary carbocation intermediate, right? Because the formation of a secondary carbocation intermediate requires a lower activation energy. Okay, so you're going to show the bromine here, and then you have the second bromine here. You have the second bromine here. Okay, and then we have to show the curly arrow from the lone pair, the curly arrow from the lone pair to this positively charged carbon. Okay, and we end up with the final product. Write an equation for the oxidation of lactic acid to pyruvic acid, the third step of figure 4.4. So in figure 4.4, okay, in figure 4.4, the lactic acid is being oxidized to pyruvic acid. So over here, the secondary alcohol, okay, the secondary alcohol group in lactic acid is being oxidized to a ketone in pyruvic acid, right? Secondary alcohol is being oxidized to a ketone. Okay, so for this equation, right, what we're going to say is CH3CHOH COOH. Okay, this secondary alcohol is oxidized to a ketone. Now what we're doing is we're removing 2 hydrogens from here, right? We're removing 2 hydrogens from lactic acid. We're going to say this guy plus O, okay, oxygen in square brackets, gives us CH3 CO COOH, right? So again, the secondary alcohol is oxidized to a ketone, and then the 2 hydrogens are removed, right? So those 2 hydrogens are taken away by the oxygen, so we get H2O. Okay? Again, this is a simplified equation. This is a simplified equation. You guys don't need to know the full equation. Okay, you can just write the simplified equation for the oxidations of primary and secondary alcohols. Complete table 4.1 to give details of the reagents and conditions used in each of the two syntheses shown in figure 4.3 and figure 4.4. Okay, so I'm just going to copy those figures down here. We have figure 4.3 and figure 4.4. Okay, and we have to just write down the reagents and conditions needed for each of these steps. Okay, so let's write this down. Okay, let's start with figure 4.3. Okay, so if we have figure 4.3, right, what reagent do we need to convert this guy to some compound that we're getting here, and then we end up getting pyruvic acid, right? So what do you think we're doing to this compound? What do you think we're doing to this compound before it's oxidized to pyruvic acid? Again, so they're saying that we get this compound, right? This is 1,2-dibromopropane. Okay, 1,2-dibromopropane. This guy is converted to some compound here. We don't know what compound that is. And then that compound is oxidized. That compound is oxidized to give us pyruvic acid. So what is this compound converted into? We know that we can get a ketone and a carboxylic acid group from the oxidation of alcohols, right? So what that means is that these bromines must be converted to OH groups first, right? So these bromines are being substituted by OH groups. Okay? These bromines are being substituted by OH groups, right? So what we have here is a secondary alcohol in the middle. Right? We have a secondary alcohol here, and we have a primary alcohol here, right? So the secondary alcohol is oxidized to a ketone, and the primary alcohol is oxidized to a carboxylic acid. Secondary alcohol is oxidized to a ketone, primary alcohol is oxidized to a carboxylic acid. We need to convert this dibromoalkane to a diol, right? Making a diol. So for that, we're going to use aqueous sodium hydroxide, right? This is hydrolysis of halogenoalkanes. The mechanism is nucleophilic substitution. Okay, we're going to use aqueous sodium hydroxide. Okay, and we heat. And then we can oxidize the diol. We can oxidize the diol using acidified manganate 7. Okay, we can oxidize the diol using acidified manganate 7 or acidified dichromate 6. Okay, so acidified dichromate 6 or acidified manganate 7. Okay. So you can say H plus slash Cr2O72 minus, or you can say acidified Cr2O72 minus, or you can say acidified K2Cr2O7. Okay, and we heat under reflux. Okay, and heat under reflux. Right, the reason we do heat under reflux is because we want to make a carboxylic acid from a primary alcohol. Okay, carboxylic acid from primary alcohol, we have to heat under reflux. If we did heat and distill, we would make an aldehyde. Okay, so you have to specify that it's heat under reflux. And then for the second synthesis, okay, for the second synthesis, what do we have? For the second synthesis, we have this, right? From ethanol, what we're doing is we're starting with ethanol. We're converting ethanol to some compound that is then converted to lactic acid, and then we get pyruvic acid. So what compound are we converting ethanol to? Okay, what compound are we converting ethanol to? We have CH3CHO, right? We have a 2-carbon aldehyde. We have a 2-carbon aldehyde here, and we have a 3-carbon compound in lactic acid over here. So how do we convert a 2-carbon aldehyde or 2-carbon carbonyl compound to a 3-carbon compound? So for that, okay, we're going to need a nitrile, right? This is the nucleophilic addition of HCN. Okay, nucleophilic addition of HCN. So what happens here is that the CH3, we have a C double bond O here, right, and an H. What happens is we have the addition of HCN. We have the addition of HCN. How do we have addition of HCN? Well, over here we get a hydrogen on the oxygen, right, and then we have a CN, right? So we have the addition of HCN, and then the CN, okay, this nitrile is converted to a carboxylic acid. Okay, so that's hydrolysis of nitriles. So in the first step, okay, in the first step, what we have is we have nucleophilic addition of HCN. So we're going to use HCN aqueous and NaCN or KCN as a catalyst, right? NaCN or KCN as a catalyst, and we're going to heat. Okay, and then in the second step, we're hydrolyzing the nitrile to a carboxylic acid. So we can use dilute HCl and heat under reflux. Okay, or just heat. And then lastly, once we have this lactic acid, we can oxidize the secondary alcohol to a ketone using acidified dichromate 6. Okay. and you can just heat and distill, or you can heat under reflux. So you can just say heat.